Thank you, Pauline. Could I add my own note of welcome to you all to this RSC lecture? It's one of a series of RSC lectures in this International Year of Chemistry, and as Pauline said, on this occasion, sponsored by GSK. But this is also an anniversary lecture. It's a celebration. So the Nobel Prize for Physics was awarded, for chemistry was awarded 100 years ago solely to Marie Curie. And I have this citation here. Citation reads, "In recognition of her service to the advancement of chemistry by the discovery of the elements radium and polonium, by the isolation of radium, and the study of the nature and compounds of this remarkable element." So I am delighted that the Royal Society of Chemistry has invited Marie Curie Cancer Care to be a part of this celebration tonight. And as Pauline said, I'm here as a representative of that organisation, having been associated with them for probably about 20 years, and as a past director of research. Now, our organisation, with its name Marie Curie Cancer Care, particularly the latter part of that name, has as its core mission the care of cancer patients. And it does that with its nurses and its doctors, its hospices and allied services. And last year, Marie Curie Cancer Care cared for some 35,000 cancer patients. It employed some 2,000 nurses to do that, delivering about over 1.2 million hours of care to cancer patients. And it's also the largest provider of specialist hospice cancer beds to cancer patients outside the NHS. But nevertheless, in the former part of our name, we are named after a scientist, and a remarkable scientist, Marie Curie. So we had our own anniversary in 2008. We celebrated 60 years. The charity was founded in 1948. And so while many of you, I would hope, will recognize the name now, what you may not know is that it was simply termed then the Marie Curie Memorial Foundation. So the founders of that organization, which is now Marie Curie Cancer Care, wanted to recognize a scientist who made such a contribution to their aims and ambition in cancer. Her discoveries, undoubtedly, in radium and radioactivity, as you are going to hear more of, and the application of radiotherapy, has saved millions of lives, and it remains a mainstay of cancer treatment now. It is still being developed in many ways, for example, with the coupling of radioactive compounds to cancer-honing antibodies. Now, we also in Marie Curie joined with the Royal Society in 2003 to celebrate Marie Curie's Nobel Prize in Physics, of course, which she was awarded with Pierre Curie and with Henri Becquerel. And on that occasion, we were joined by representatives from the Institute Curie. And as you may know, the Institute Curie evolved out of the Institute du Radium, which Marie Curie had driven forward from there to the Curie Foundation and on to the Institute Curie. And we were delighted to have an interaction between our two organizations then, and we continue to do so at times thereafter with scientists visiting in Paris and at the Marie Curie Institute in London. Now, she never forgot her Polish origins, but of course it was in France and in Paris, at the University of Paris and at the Institute Curie, where she made all her remarkable discoveries. And so I'm particularly delighted, therefore, that tonight we have a representative from France in Dr. Serge Plattard from the French Embassy. His title is officially there. He is the Science and Technology Counsellor to the French Embassy, but he is a scientist by training. He graduated with his PhD in 1973 from the University d'Orsay, went on to work in low-energy nuclear fission, I believe, and nuclear astrophysics at the French Atomic Energy Commission, and from there he was seconded into the Ministry of Foreign Affairs for a while, returning back to the Energy Commission in the Directorate of Planning and Programme for the long-term planning in the Eureka programme. And I think that started in about 1987. his career in the administration, planning, development, and cooperation of international science. He then served as Deputy Counsellor for Science and Cooperation at the French Embassy in New Delhi in India, going on to Tokyo as Assistant Director for Scientific and Technological Cooperation. From there in Tokyo, he went on to the French Mission for Science in the United States and acted as Counsellor for Science and Technology at the French Embassy in Washington. From there, back again to France, and here Director of International Relations at CNAS, the French National Space Agency, and Vice Chair of the Committee for International Relations at the European Space Agency. And then from 2004 to 2008, European Space Policy Institute, which he helped found and served as its first Secretary General. He's a founder member of the organisation Euroscience, and he's a corresponding member of the International Academy of Astronautics. I was particularly, in reading Dr. Plattard's biography, CV, to see that he was awarded what I believe to be one of the most colourfully named accolades that I have come across. In 1994, he was awarded the Golden Rays in the Order of the Sacred Treasure, a particular Japanese distinction, obviously, from his time there in Tokyo. He's also awarded a Knight in the Order of the Legion d'Honneur. So it's with great pleasure that I invite Dr. Plattard to give this evening's RSC lecture entitled The Three Lives of Marie Curie.
Well, good evening, ladies and gentlemen. And first of all, I would like to thank the Royal Society of Chemistry and the JSK for making this evening possible. And I would like also to thank very much Pauline and Professor Hoover for the very kind words you said about me. Thank you very much. So I would like to, in this commemorative year about Marie Curie, as you know, probably she won also a second Nobel Prize in 1911. And this is, I think, too loud, but never mind, okay. It's up to the audience to appreciate. And also because it is the International Year of Chemistry, so I think she's particularly the right person to be honored. So the title of tonight's talk is, there's a kind of echo. It's not very pleasant for me, but maybe for the audience too. Why it's entitled The Three Lives of Marie Sklodowska-Curie. The three lives, because when you look at her work, it's very clear that she spent a lot of time, first of all, as a pure scientist. Second part of her life was certainly more applied to develop applications, with maybe lessening a bit the side of pure science. And there is a third part, which maybe is not very well known, but was very important for her and for her daughter, Irene. It's the role, I will come back to that, is the role she played during World War I as helping surgeons in a very particular way, which enable to save tens of thousands of lives, maybe 100,000 of lives, and I will explain why. So she was really focused on this is really three parts of her life. Her life, also when you look at it in a sort of transversal way, she was always, I would say, motivated at least by three aspects. First of all, she had a lot of genius, and it helped her during her whole life, or her whole three lives, I would say. She had a lot of obstinacy. She really wanted to get things done. She was a very strong woman. And third, in several occasions of her life, she enjoyed serendipity, which helped her a lot. So this, we can find that through all her life. So she was very gifted in that way. I'm starting by the end. I'm starting by this very important memorial ceremony, which President Mitterrand, a few days before he left power in 1995, wanted to have at the Pantheon. The Pantheon is a memorial place in the Latin Quarter of Paris where I would say the rest of the very important people for France have played a role in building up France politicians, writers, scientists, whatever. And Marie Curie was the first woman by her, I would say, capacity to be buried in the Pantheon. There is another woman, which is the wife of a chemist, Madame Berthelot, who said that she would never be separated from her husband, so was allowed when Berthelot would dare that he would come with his life and with his wife. And Marie Curie is the same reason. Pierre Curie joined Marie Curie in this ceremony. And it was meant because Marie Curie is the first woman who obtained a doctorate from French university. She was the first woman who got a full professorship at the university in France. She was the first woman who graduated first from Bachelor of Physics. She was the first woman to graduate first of the competitive examen to be teacher in secondary school in France. She was the first woman to obtain a Nobel Prize, and she was the first woman to obtain a second Nobel Prize. So this had to be honored in a way, and that's the reason of the ceremony. And the speech of the ceremony was essentially held by Mitterrand, of course, and by another Nobel Prize, a French physicist, Pierre-Gilles de Gennes. So just to map out who is this woman, which, by the way, you all know is a Polish, and her birth name is Sklodowska, and she born so in Warsaw at this time in this street. The old house is on your left, and the new house is on your right. And she get a very, I would say, standard childhood in a country at that time which was occupied by three major powers: the Austro-Hungarian Empire, the Germans, and the Russians. And Warsaw at that time was under Russian domination. Polish was absolutely forbidden for teaching. For speaking in the streets, you had to speak Russian. And this certainly is the start of her continuous rebellion during the whole life. She wanted to speak Polish, and I have no time to give you a few anecdotes, but there are a lot of funny anecdotes where in some cases she risked, I would say, not the life of her parents, but certainly the salary of her parents, and in particular of her father, who was a teacher in science and mathematics in Warsaw. This is Marie Curie when she was 3. This is her elder sister who died of, I can't say the right, of typhus, if you say it in English. And this lady, Bronia, will play a key role during almost all the life of Marie Curie. We'll talk about that later on. She finished secondary school at age 15, and in Poland at that time, all over Poland, whatever was the occupant, ladies, girls were not allowed to go to university. So she decided to spend time as a governess, or as an au pair, or as a teacher in several families, and this lasted from 1983 almost to 89. And so she went in several places in Poland. She had good fortune and misfortunes, but this was a way to earn her life. And she did that because around 85, she started a sort of bargain with her elder sister, Bronia. Bronia wanted also to leave Poland and wanted to study, I would say, medical studies in Paris. At that time, Paris was attracting was a strong attractor around the world, in Europe at that time, with the UK, of course, and Germany. But many, I would say, students from Central Europe and Eastern Europe would like to complete their studies in Paris. Paris also was spotted as a sort of center for young revolutionaries, young rebellions, and so the Poles, with the political situation they were living under, wanted to go to Paris. So her elder sister went to Paris for the studies, and those studies were essentially paid by the money Marie Sklodowska at that time, was making as a governess. And the deal was that when her elder sister Bronia would finish her medical studies in Paris, then she would earn a living in Paris, and then Marie could come to Paris, and Bronia would pay for her studies in Paris. So it's a long-term planning, because it took almost 10 years, but I mean, the two sisters got along very well, and they managed to do that. Their father complemented their living in a rather small amount. So this is one example of the places she was staying in the countryside out of Warsaw. This is Marie in 1995, so we're jumping quite strongly in time. I'm going to give a few details. So she moved to Paris. She decided that she could move to Paris in 1892, and she entered the Sorbonne 2 days after she arrived in Paris to start a bachelor in physics, which she completed in 93. I'm sorry. She passed brilliantly first, and the year after, she considered that she needed a bit more for math. So she did an extra year in math, and she completed the exam and passed it second. At that time, she wanted to begin to think about what she could do as a doctorate. She was very interested to carry out some research. She found some work on measuring some magnetic properties of metals, but she couldn't find a place to do this kind of work. And it happened that she ran into a Polish physicist who was working at Paris, traveling in Paris, Professor Kowalski, and he told him, well, I know a fellow at the École de Physique et Chimie de Paris, he should help you. And so this person organized a meeting in end of 94 between Pierre Curie and Marie Curie and Marie, and then they fell in love quite quickly. They married in 95, and this is how she was at that time. So she could complete her studies. She had time to marry in the summer of 95. This is probably a picture which was taken shortly after the marriage. They decided to do their wedding trip on bicycle, and this is probably the day of the marriage that the picture was taken, and they left for a rather long time. At that time, it's less the case today, but at that time, the vacations of academics in France were very long, very long. So here we're in 95, and I think it's important to know the family Curie. The two brothers, this is Jacques and this is Pierre. The two brothers, I'm sorry, this is Jacques and this is Pierre. It's important because the two brothers were physicists, and they're working very closely together. And this person, which is Dr. Eugène Curie, will play a very important role in bringing up Irène, the first daughter of Marie Curie. We'll see why. It was a fantastic period at that time in physics. We were entering a complete new domain, I would say, of invisible physics. The Maxwell equations were working properly. Hertz did very important work on electromagnetic propagation, and we were having also beginning to understand how to send messages with electromagnetic waves. The Branly people, the Marconi people, those people were very active in that time. And as you certainly know, totally by accident, the X-rays were discovered by Röntgen, who was not a very famous physicist, who didn't enter the proper, I would say, trails of the usual brilliant physicists in Germany. In about Christmas in 95, he asked his wife to put his hand somewhere on the beam of X-rays, and this is what he found on a screen. Of course, you can see the ring of the wife. The hand stops roughly here. Huh? This is the hand, and the fingers stop roughly here. So X-rays were absolutely booming, and a few months later on, in another, I would say, domain, a French physicist, very well known, Becquerel, found also by accident that a piece of uranium that he had sealed from the light. He was carrying out research on luminescence, and the idea was that if you irradiate materials with light, at some point the materials will give back the light, and you would have some emission of light, which a very long time constant could be days, months, or years. Okay. So he was trying things with uranium salts, and the weather was bad in Paris, so he decided to wrap those salts together and wait a few days that the sunshine could come back. But he was so anxious to look what was going on in the of this material that he put a photographic plate, and he had wrapped the uranium salt with a malt cross, which maybe you can't see here. I'm sorry, there is a cross normally here, but you maybe can more or less guess. It's difficult on this slide. It's an original slide. original picture, and he found that the photographic plates were impressed, you don't say impressed, were marked by sort of light, because silver chlorine turned black, and this was absolutely abnormal because there was absolutely no light who came on the radium salt. So he continued to work on that and made sure it was not a spurious effect, and so he discovered a new, I would say, mode of liberating energy by matter, but no more than that. And the rays who would produce this effect on a photographic plate were called uranic rays. There was no other name because it was uranium salts. Marie Curie looked at that and said, well, this is interesting to work on that, but I don't want to repeat the experiments of Becquerel. I want to do something absolutely new. And so she decided to study systematically uranium. Uranium ores, components of uranium, and see what's coming out from this material. And to do that, that's where serendipity enters. To do that, she had to measure, because those materials were emitting, I would say, were ionizing the air and producing current. So she needed to measure a certain current, which was a very weak current. And serendipity comes because almost 20 years before, the brothers Curie discovered piezoelectricity, meaning that when you apply a force on certain faces of a crystal, you produce electricity. And they developed a tool called an electrometer to measure minute quantities of electricity. So the game was that if you could counter the current that was produced by those mysterious rays by creating an inverse current, by applying pressure on a crystal with a calibrated force, which was done with weights, you could balance a Wheatstone bridge and measure exactly what was the current. And what they discovered very quickly is that the current you would measure was proportional to the quantity of matter, which is very important, and that the matter was, the current you would measure was independent of the chemical form of the uranium. It was salt uranium, uranium coming from an ore, pure uranium. You would measure with the same quantity of uranium, always the same current. So that's where Marie Curie was a genius. She stated that what was measured was not linked to molecular or atomic properties. It was coming from the atom itself, whatever be the arrangement of the atoms. And at that time, the image one head of the atom was a ball, was just a global ball with no details. But it was conceptually very powerful. So she carried out measures and measures for a long time. It was a very new phenomenon. So Pierre, who was still working on magnetism, stopped his work on magnetism and joined Marie in her lab to try to understand more, I would say, deeply what was going on. And they decided to do the work in a lab. And at that time, research was absolutely inexistent in France. There was very little care for research. So eventually, in a Parisian chemical and physical school, they were awarded a shabby shed where they could do their experiments. And what they succeeded to do was that in 1988, they discovered that even using depleted ore of uranium, you would still see, I would say, those ionizing radiations. And when you were purifying this ore, you would have more and more intensity. So the second concept was that very likely uranium was not the origin of this uranic so-called rays. It was a new element. And so that's how they stated the existence of a new element. You can see this is a photocopy of their lab notebook. You can see here a PO, which is for polonium. They decided that this element would be called polonium to remember, of course, the Polish origin of Marie Curie. And indeed, they stated that. And at the end of the year, they discovered another element, which was radium, was much more intense in the very depleted ore of uranium than radium. So it was clear there were two new elements discovered, but the chemists, sorry to say it here, but they're right, the chemists don't believe in that. Chemists believe in new elements when you can measure their weight, so you can classify them in a Mendeleev periodical table, and it means something. Otherwise, those are indirect effects of elements, and it's not a proof for a chemist. Well, so she knew she had to prove that this element, radium and polonium, did exist, and they were embedded for the polonium. For the radium, it was embedded in barium element, which was well known and easily treated by chemistry, and for polonium, it was embedded in some bismuth, very like mixtures. So she worked on that, but she realized that to have a measurable quantity, she needed an enormous quantity of depleted uranium. And the calculation came very quickly. If you want to have sort of a 0.1 gram of radium, you would need about 10 tons of depleted uranium. Where to get this uranium? To make a long story short, with their connections, they managed to have uranium, depleted uranium, and waste of uranium shipped from a mine in Joachimsthal in southern Czechoslovakia, shipped to Paris for almost free. And the whole work of Marie Curie from 1999 to 1903 was to purify those amounts of ore and to come out with a ponderable quantity of radium, which she succeeded. Sorry, it's not the right one. Which she succeeded. I'm going to skip this. It's how you produce, how you can get radium from uranium, and you can have the same thing also coming from thorium. Marie Curie showed that apart thorium and uranium, all the other elements she tested, about I think more or less 50, there was no particular emission of ionizing radiation. So she concentrated essentially on uranium. So in 1903, she succeeded. They were able to have a measurable quantity of these new elements, who were very radioactive, and they didn't care about the health. They were constantly irradiated in the laboratory. There was quantities of particles of radium, of uranium, who were polluting the tables, the instruments, the walls, the floor, their clothes. And we can still, when you go to the museum, you can still measure the radioactivity of the elements of the laboratory at that time. So it was a really dirty job. But they didn't believe that the radioactivity was something dangerous at that time. In 1903, the Nobel Prize for Physics was awarded to Becquerel and Pierre Curie, because they were the two considered. Becquerel discovered the phenomenon. Pierre Curie worked on that, but Marie Curie was not mentioned in the first, I would say, advertisement or correspondence in the summer 1903. And Pierre wrote to the academia in Stockholm and said, I'm sorry, I will not accept to be awarded the Nobel Prize if Marie Curie is not in. She did essentially the job. I did my part with the equipment, but she did the job, so she should be awarded also. And eventually she was awarded the prize for Nobel Prize for Chemistry, so first woman in 1903 to obtain it. But it happened, a funny thing that has never happened since. Both of them, Pierre and Marie, didn't went to Stockholm to receive the prize. They didn't went there because they considered they were too busy continuing to find out more details about what they had discovered, so they didn't show up. So it's Becquerel who went to receive the prize and explaining what happened. And it's only in 1905 that Pierre Curie accepted, because he had a bit less of a job, to go to Stockholm and give the traditional lecture. And Marie was very weak also in 1903. Certainly it was the first sign of irradiation on her health and on her general state. So they didn't show up. They continued their work in the 1903, but they were spending the essential time of the day and part of the night in the laboratory to try to produce more radium and to try to understand the properties of radium and to try to understand also how radioactive decay works. And they were much helped in that by two eminent physicists, a New Zealander who became, I think, British later on, Rutherford, and Frederick Soddy, who was a brilliant British physicist who understood more theoretically what was radioactive decay. So because she was off very often from her place, she left her children to the grandparents. And Irène, that you can see here, has spent a lot of time with his grandfather, who was a physician, Eugène Curie, and all the scientific thinking, the scientific discipline, the sense of observation Irène had, she gained it from her grandfather in those very, very early 1900 years. The education also of the two children were, I would say, geared by Marie Curie, who she didn't believe in standard public schools. She decided that they should have, for her daughters and for a few others, an elite school, and the elite school would be to make the kids travel from one professor to another professor, but the professors were potential already Nobel Prizes. And they would lecture the children on, and there were also musicians, sculptors, a lot of physical education also was given to the children. And for 2 years, Eve and Irène had this kind of treatment, and then they entered the French system, but of course with a background very different than their comrades from the classroom. The same time, you can see the two girls. So this is the new one, Eve, who will live almost 100 years, and Irène. So I pronounce it all with a French name, so for me it's Irène. At that time, Marie Curie understood, and other people understood, that there were applications for radioactive elements, and in particular applications in medicine. You could organize the radium you would have, put it into some needles, and you could use the needles through patches to try to cure some cancers or some lupus, skin diseases, and it worked in some cases very well, but of course you were exploring a totally unknown domain. And you would use also gas capsules, who were very radioactive, of radon, radon being the daughter of radium, produced very quickly, very handy to manipulate in capsules, and you can also launch the capsules to treat, for instance, other kinds of cancers, as you can see here. So the side of use of radioactivity, of irradiation to treat cancer was developed very strongly and very quickly, not by Marie Curie itself, by her lab and by her people, doctors, physicians who understand what could be the use of radioactivity. And at that time germinated a very simple idea that somewhere we should have in Paris or in the countryside a rather larger lab which would produce radio elements, but also by the lab you would have a biological or medical facility to manipulate those, I would say, samples, to calibrate the radioactivity of the samples, so to use them properly for therapy for different diseases, in particular cancer. This was the birth of what was called at that time radium therapy, then it turned out to be radiotherapy, and also Curietherapy. Those three names were used at that time, and so it became to be very successful. Of course, the effects of the cure were not, the collateral effects were not pretty well analyzed, so you could have, unfortunately, also very bad results. But it started there. This time also there was a folly on radio something, radio water, radio cream to put on your face, radio suntan, all kinds of things which were usually not radio of nothing. It was just a charlatanism, but it was selling like mad, radioactive soaps whatsoever, which were not radioactive or had a tint of radioactivity, but radioactivity was the miracle. It could cure everything. It could rejuvenate you. I mean, it was absolutely fantastic. But it lasted only until the 1910s, 1912s, with this intensity, of course. You had the thermal cure also with radioactive water in Eastern Europe, of course, but there was also other facilities. At that time also, Marie Curie, because she had not enough work to do in her lab, was agreed to become also a professor at the École Normale de Sèvres. This is one of the two major elite schools for science and humanities in France, with the École Normale of Rue. And you can see on this picture, she is with Paul Langevin. Paul Langevin was a brilliant physicist. He was a student of Pierre Curie, and Marie Curie taught only to this girls' school, and she loved to teach also and to carry out research. Then there is a big bug in the life of Marie Curie. It's called the Langevin affair. I haven't mentioned that in 1906, Marie Curie lost Pierre Curie, who died of a fatal accident in Paris. A cart rolled on him. The cart was going extremely fast. He didn't see the car. He crossed the street and he was tumbled and died almost instantly. He was already at that time very weak, very sick. Probably he was a neurasthenic, and probably he had also a problem with red cells in his blood. And so he was a weak man, and maybe he was not sufficiently attentive when he crossed the street, and that's why the accident happened. So Langevin, who was very close to Pierre Curie and to the Curies, took care gradually of Marie Curie, helped her in sorting up all these papers, and consoled her, and they were very close friends, and the relationship turned more like a love affair. And the press was absolutely infuriated against Marie Curie, despite her Nobel Prize. She was a stranger, the Polish, who came into France to assist to the discovery of radioactivity. She was the one who destroyed the French family. She was a hopeful girl, and her name, Sklodowska, and her second surname, second name was Salomea, proved that maybe she was a Jew. So it was absolutely unacceptable, and how dare this woman, in addition, wanted to enter the Academy of Sciences. This was really impossible. So she had a very tough life. We can't say today if the story is fully true or not, but there is a strong indication that it was indeed true, in particular reading at what the son of Paul Langevin said. So there were awful years for her, and she became depressed. She wanted to live out of Paris. And things got worse. Because the same year she knew she could have the Nobel Prize of Chemistry, and the prize would be awarded to her alone. But the Academy of Stockholm heard about this affair and wrote to her in November. The prize is usually awarded for the anniversary of Nobel, so it's around December 11, and wrote to her and told her, you shouldn't show up in Stockholm in December, because unless the judgment of this affair is not sealed, we do not accept. And she wrote to Arrhenius, who was a famous chemist, but he was a chair also of the Academy. No way. I mean, I've been awarded this prize for the work I've done in chemistry, for the quality of my results. Private life has nothing to do with that. So I'll show up on December 6th. And she showed up. She got the prize. Just also, she learned that the Academy would possibly not give the prize when she was attending the first Solvay Conference, which was a conference started by Mr. Solvay, who was a Belgian, as you know, well-known chemist also, industrial chemist, who wanted to gather every year, or every two years, I can't recall, or 4 years, I can't remember, I'm sorry, the top of the cream of the scientists at that time in the world, who essentially was Europe and the US at that time, in disciplines of physics and mathematics. So she was the only woman here, attending here, and on this picture where she learned the bad news, the fun thing is Paul Langevin is here with Einstein. There are a few other guys, Rutherford at the back here, and I mean really top people who were there. And so she left the conference Solvay and flew to Paris and to try to get organized. So she gave her lecture to obtain the Nobel Prize of Chemistry, and the citation says, as it was just remembered, for the discovery of isolation of radium and also for polonium, but they are more accurate on radium than polonium because it's very difficult to isolate properly the polonium. The first Nobel Prize she had in 1903, which was a physics prize, didn't mention nothing about polonium and radium, which were already, for Pierre and her, no doubt they were discovered. She got the first prize in physics only for discovery of radiation and ionizing radiation coming from matter, and not more specific than that. So that's why Becquerel was the key actor in the first Nobel Prize. She, as I mentioned, decided to have this lab of chemistry, physics, and medicine started up in 1908. And as usually in France, the fight started between administrations. We're not the only country, but we're good at that sport in France. Marie Curie was with the university. She became full professor in 1908 and previously succeeded to Pierre in the university. And the university said, well, we're going to build this laboratory. And Institut Pasteur said, no, we're going to build it. And so the fight started, and eventually they joined forces to build this institute, which was completed just before World War I in 1913. And so both Marie Curie and the new fellow, who was a physician, very acquainted with radioactivity and radiotherapy and understood the benefits of radiotherapy, Dr. Claudius Regaud, they started the institute, but it really ran only after the war, not really before. But they had a place, and the place is this one. Currently, this picture was taken early this year, and this is the institute when it was completed in the 20s. Okay. The war started, and Marie Curie, when the war broke, the first thing she did, she took the gram of radium she had and put it in a bank vault in Bordeaux. Alone, she boarded a train from Paris with tens of kg of lead protection of her gram, went to alone, but held by an official eventually in Bordeaux, to store and put in a safe place her radium, went back to Paris, and decided that the war would be the war, the work would be difficult, but she wanted to help. And she understood that X-rays, properly used, could save a lot of lives and could contribute to pre-surgical diagnosis with soldiers who had some shrapnel or some pieces of shells in their body, and instead of just cutting where you don't know exactly where it is, if you can do an X-ray, you could pinpoint more accurately where the surgery should take place. And so she did that on 2 stands. She succeeded in installing X-ray machines on 20 petites Curie, little Curie, who were cars of, I don't remember the brand, if it's Renault or Citroën, who were gifted to her by French rich ladies who wanted to help for the war. And in addition, she, with Irène, when she was 18, installed 200 fixed X-ray machines and diagnosis in hospitals on the trenches near the front. And it is, I would say, evaluated that having X-rayed so many wounded probably helped between 10,000 and 100,000 lives because the diagnosis was put properly. So it's quite impressive that she decided to stop everything and to help people. The war ended, and she began to work back in her laboratory, combined with, I would say, the other facility for biomedicine. And in the 20s, both Marie Curie and Regaud thought that they should do more than just prepare elements for cure. They should maybe have very close to this laboratory a facility to cure people and to bring people in and benefit of the radiotherapy on the spot. So a Fondation Curie was created, and donators like the Carnegies, like Edmond of Rothschild, that was Henri of Rothschild, and few others gave money to start this hospital, so to speak. And this hospital, it's not the same which exists today, but on the place I just mentioned, in the back, there is the Hôpital, the Institut Curie, where it's a cancer treatment center, one of the largest, I would say, in France, which works very well. But you see the legacy of the Curie through 1 century continued right on the spot. So in the 20s, her lab began to build some instruments for radiotherapy. You have 2 examples here, sort of cobalt bomb here on the right, and a more localized instrument to cure some, I believe, brain cancer or brain tumor. So it started this way until the 1940s. Her problem was that she had only 1 gram of radium, and so was not enough. At that time, the Americans started industrial production of radium, and they had 50 grams. So she was very weak, and she couldn't produce sufficiently, I would say, elements for the needs. It happened that she was interviewed by an American journalist, very famous, Mrs. Meloney. Usually, Madame Curie would never accept any interview. And this lady managed, because they were the same kind of temper, to interview him. And she told her, well, what's your problem? You should come to America, and if you want more radium, I mean, we're going to collect money in the States. You're going to tour the States, and you will have radium. But who will give me the radium? Well, the American woman will be happy to give you 1 gram. Well, she decided then that she would go to the US. She was extremely popular in the US. This lady secured and managed to secure that the New York press and the American press would never talk about the Langevin affair, because it would spoil completely the image, of course, of Marie Curie in the States. And the press kept silent and behaved properly. So she went to the United States and met President here, at that time was President Harding, who she was received in all kinds of places. She was received at Columbia University. She traveled along the country and eventually got her gram and shipped back her gram to France. And she was so exhausted during those trips that in some circumstances, the 2 girls, Irène and Eve, would go for Marie Curie and show up in some places, and she would stay at the hotel. And she spent, I think, 3 months in the United States and went back. Then she had the idea in the late 20s that she would need extra radium for another institute. She was Polish, and she wanted also to set up a radium institute in Warsaw. So she went back to the United States, again helped by Mrs. Meloney. The same system worked, and President Hoover gave her a check to purchase another extra gram, which was making around 3 grams for France, plus something. But the US were running in the range of 100 grams at that time, and so they did all kinds of research with radium, which we couldn't do in Europe. So this is the Warsaw Institute, which was set up by her sister, the famous Bronia, who was a physician, who returned back to Poland, I think in the 1910s or somewhere there, and started a sanatorium to cure tuberculosis in a place in the Carpathian Mountains in Poland, and helped her sister to set up this institute, which is still running. Again, I wanted to show here the reputation of Marie Curie in those very famous and important conferences. You can see the names here who are really the top of the physicists at that time, and you can see also here that she's still the only lady in this meeting, where the Einstein is not in this photo, but Paul Dirac, famous British physicist, is here, Planck, Schrödinger, Rutherford, I mean, everyone is there. And to continue and to see how the family is progressing, here we are in another Solvay Conference. So this is 1 year before the death of Marie Curie. There she is here. Her daughter is here. There she is. Her daughter is here. Paul Langevin is still here, of course. This is the main competitor, Lise Meitner, a German chemist, the main competitor of Irène. She co-discovered the fission of nuclei, which the Curie didn't. Behind here, Irène, her husband, Frédéric Joliot. This is Schrödinger. I mean, you have extremely good people here, but you see that the women slowly are penetrating this cenacle, but led by the Curies, except for Lise Meitner. Yes, you're right. Irène walked into the footsteps of her mother. She worked at the laboratory. Frédéric Joliot, who became her husband, was hired by Marie Curie. He was a very dynamical man, started a new type of physics, not only looking at passively radioactivity of nuclei, but bombarding nuclei with alpha particles and other particles, and see what you could gain by bombarding a nuclei, what kind of new matter you could build. And it happened that it did. This is what happened later on. I will show that on a picture. Marie Curie and, Irène and Frédéric discover artificial radioactivity few weeks before the mother of Irène died. This is, you can see the contrasting picture of Marie Curie in 1932 compared to the picture I showed when she was in Paris. She was really a used woman, a tired woman, presumably already having leukemia, on the start of leukemia. She could be very weak, and she is pictured here at the Institut du Radium looking at her garden. Her garden, she loved flowers, she loved trees, and at that time she decided maybe she would retire and just do gardening. But she had a compelling obligation she wanted to complete, is to finish her new treatise on radioactivity. And I'm a bit moved looking at this picture for the following reason, that the garden keeper and the mechanic of the laboratory, which was called Georges Rabot, it happens that when I started my thesis in Saclay, I met the man. The man was almost 65. He was about to retire. He was cycling every day, tremendous shape. And she, of course, had incredible stories to tell about Marie Curie. And it happens also that when I was working at the French Atomic Energy Commission, my family knew Bertrand Goldschmidt, who is the last person that Marie Curie hired in her lab in the very early 1934. So my connection is very indirect, but it turns out it's this way. So it's always moving for me to talk about this period and this lady. This is a picture showing Einstein with Marie Curie. They were very, I wouldn't say friends, but they had a very big esteem one to each other. Their children and them spent vacations in the Alps in 1913. And Einstein had different opinion on Marie Curie. Well, the first one is a bit a cold one. This is when he met her first, because she was not very talkative. And the last one, of course, is fantastic. This is when he was living in Princeton. He wanted to show up at a memorial ceremony for Marie Curie, and he said those fantastic words that there was absolutely an incorruptible lady, that probably she suffered and she worked on experimental physics like maybe no one worked like that for 4 years, which was the case between 1903 and 1899. So it was very, I would say, admirative of Marie Curie. And both of them, when the League of Nations was created, there was a commission on intellectual and cultural cooperation. And both of them sat on this commission to try to build up the necessary bridge to have more fluidity in the circulation of ideas. Marie eventually became vice president of this commission, and Einstein quit the commission because he thought the commission would go nowhere. So I think he was right. This is one of the last pictures of this presentation. This is Irène receiving the Nobel Prize, so the next generation receives Nobel Prize, with her husband Frédéric, given by the King of Sweden, for the discovery of artificial radioactivity. The story says that, of course, it's in 1935, the mother was dead, but before she died, in early 1934, Marie was informed of the discovery of artificial radioactivity, and she understood and she grasped very quickly what this could lead to, which is absolutely enormous. So she was certainly happy that her daughter could do that, and her daughter was very happy that she could give this present to her mother. Very happy because the Joliot-Curies missed two important discoveries which they had at hand in the lab, but they didn't see the evidence. They missed the discovery of the neutron, was discovered by Chadwick, a British physicist. They missed it. And they missed also another discovery, the discovery of positrons, positive electrons. They could measure them, but they didn't see them. But eventually, they succeeded in discovering artificial radioactivity at once. Irène had two sons, one son and a daughter. She is a physicist. She's still living. And he is a physicist. I know both of them. She was a very brilliant physicist, a nuclear physicist. And but of course, she died also, presumably, of leukemia also in the mid-1950s. I'm sorry, something happened, but I think it was the last slide. Yeah, this is his last slide. You can see the daughter and the mother and how, I mean, brain almost ruin physical is the mother, is presumably taking in 1933, and obviously Irène was ready to take over, and she became the head of the lab just before the war. So I think it's an incredible story. It shows again the pugnacity, the willingness of this lady to get things done, and she got tremendous things done. She also has opened, I must say, a completely new field in physics. I mean, the fact that you could understand radioactivity leads to nuclear spectroscopy. It leads eventually to fission. It leads to, of course, the creation of radio elements, to applications on radiotherapy, in biology, in agriculture, in many places. So is it a total serendipity that she discovered that at that time? We don't know, but I think the blend and the mixture took place at the right moment. There were a number of ingredients who could coalesce at the right time. Maybe someone else could have discovered that, but it happened that way. And I think we have to pay tribute to Marie Sklodowska also, because it's very often in the Western world we talk about Marie Curie. Of course, in Poland they talk much more about Maria Sklodowska, but I think it's Maria Sklodowska because she arrived in France when she was 24. And when you are 24, I mean, your brain is pretty much formed, your sensitivity, your sense of observation, your reactions, you're almost I mean, you then benefit of the different occasions, but she was trained, formed, educated at hard times in Poland, and she was extremely brilliant, like her sisters and her daughters. Thank you very much.
Thank you very much. An absolutely fascinating lecture, and I wonder if there are any lessons from that story for today's science, but maybe that's open to you. So, as on these occasions, Dr. Plattard is happy to take questions. There are microphones that will be roving, and if you would not mind, put your hand up and then perhaps stand up, and if you could give us your name and affiliation, if you wouldn't mind, and it will certainly help. And please do use the microphone. So please feel free. Well, there's a silence. Well, could I start off and just ask a question? If with that tremendous knowledge that you have of the history across the disciplines, what lessons do you think we have for the support of modern science from the story of Marie Curie and her drive in pure science and the fact that it has delivered unforetold benefits across many disciplines?
It's a tough question. Try to be extremely frank and direct. First of all, the conditions in which science was developing at that time, of course, is radically different than the conditions we have today. The fields were narrower. The number of people involved in science were very few compared to today. There was no mass education. The politician didn't grasp really the interest of science. So people who were bright, who could manage a minimum funding, could work. Today, it's more, in some cases, I would say almost a factory. You have to produce or you die, publish or perish. The easy things, quote unquote, have been already discovered. So the efforts are much more complicated. It's much more a teamwork, international teamwork. You have deadlines. Competition is very harsh. So the whole picture is totally different. But what we should maybe, despite this tremendous difference of landscape worldwide, what we should really look at is at that time, people could carry out fundamental research and had a certain liberty, freedom to find the result, to go ahead, to move ahead. They would autodiscipline themselves. They could work like mad. They knew there was competition, and in the 20s, the competition in Europe was very strong. The Americans were coming up. The competition was very strong. But people would work and get the result at the very end, and where they were not, I would say, too much trouble by money because they didn't need too much money. Today we need much more money. And the lesson we should have today is when you have extremely good teams, you should fund them. Despite the fact that you're not sure they're going to succeed, you're not sure about the result. But if they are good, just fund them and facilitate those teams by helping them to start up seminars, conferences, travel internationally the more they can to get acquainted with other people and find things. Today, when the Gates Foundation, in some cases, I would say, is ready to fund some research, there is one type of application which is absolutely incredible. You have to fill in a two-side page of your ideas with no references. They don't care about reference. They're going to compare your proposals and with others and give it to some referees worldwide. And if you are really good, you get it. And you get a significant amount of funding because you have the bright idea. So today, what maybe, I wouldn't say is a threat, but what bothers a lot of scientists today is a sort of control of what you're producing, very tight control. You know, it's like a company. Every trimester, you have to give results. In some cases, you can't. Possibly you cannot. And if you have to have new discoveries, new inventions to bloom out, in some cases you need to give time and accept to give time because it's, first of all, it's for the knowledge. You never know the applications that will come out and the benefit for society. So it's a sort of, I would say, insurance premium that the society should pay to scientists and say, we accept to pay so much for you guys to find something to enrich the knowledge of society and possibly maybe to have applications. We have a fantastic case that you all know in this room is the discovery and the applications of the World Wide Web. This is absolutely discovered at CERN, a machine for fundamental research, because it was more easy for scientists to be in different places in the world and to consult the same kind of files and work on the files and share the files, that the whole thing started. And of course, we know that there was a British scientist who played a key role in doing that. Okay, this was not planned, it was not funded, it happened. It happened because it was a fantastic environment of fundamental research where this need showed up and clever people would be able to make the necessary work to make it work possible. But you wouldn't fund right on the start, I'm going to fund World Wide Web research in 1989. No one would do that because, well, people had no idea. So when things, and when excellent places are working, when things are happening, just fund them, let them happen, let them work, new things will come out.
Very well said. What a laudable message from a fantastic story. If you could just wait, the microphone will help. There's one here at the front. Thank you very much.
Okay. Hello, my name is Douglas Hutchison. I'm retired. I was interested in your talk about the Marie Curie being gifted and having the obstinacy and also serendipity. You may not know, I'm actually blind, and I'm a great believer in serendipity because our chances of finding something are not the same as a sighted person. If you're blind, you have to be lucky in getting somewhere. Can I ask you, in a society that we have, certainly in the UK, which costs everything, which puts a price on everything, yet doesn't appreciate value, how would you measure serendipity?
It's a very tough question. Is there a marker to measure serendipity? I haven't really thought about that. I don't know how to measure it. But maybe, I'm not answering your question because it's difficult, but maybe could try to explore this, the following avenue, is to create conditions where the likelihood of serendipity increases. That we might try to do that. And this is maybe more quantitative and we can do it. we can do it in certainly bringing together, in some occasions, people of a very different background, very different sensitivity, and I think, although I understand what you say in the British society, but I think in some universities in these countries, particularly the ones which have colleges, where people of very different disciplines get together, of different backgrounds, of extremely different nationalities, can get together, I mean, crossing ideas, new things can germinate, and things can happen. That's one part of the equation. The other part, I think, is directly related to education, is to make young people understand that they should be extremely open to what happens around them. Not self-centered on a particular, I would say, issue or movie or type of reading, but how in the education system you can make that people are, I mean, there's certainly you acquire some, I would say, capabilities, and you are born with also some capabilities that you just can't change. But if you are in a universe, in an environment, where you're exposed to different people, different things, different reasonings, maybe different languages also, I think it's important, and was the case of Marie. Marie was fluent when she was young in Polish, German, and Russian, and was learning English when she was 15. So, you know, it makes a certain gymnastic with your brain. It certainly enhances your curiosity to look somewhere else, to try to meet different people. And I think to be more interdisciplinary and have the occasion with youngsters to make them travel, to expose them to other milieux, could help to be more alert. And when you are more alert, maybe you are more curious to find something else, and then maybe serendipity can occur. But educating people in some, I would say, definite trails, or even worse, in some silos, in some disciplines, I think it's very bad. I mean, it's the chance that serendipity, I would say, I want to say positive serendipity, but this is almost a pleonasm, occurs, are certainly much lower than if we try to do what we're doing, what I'm advocating for. But I understand that today, when you look at the education system worldwide, it's complicated. Yet, in your country, in your colleges, you have the possibilities. When you look at the top of universities in the Gulf region that are trying to be set up, bringing people from all over the world with different academics or different nationalities, different backgrounds, you know, people who have gone through this type of education, which will scatter afterwards in other countries, might present, I would say, possibilities of being more serendipitous. But your question is a very complicated one and very interesting one, because indeed, is it measurable first? And second, how you measure it? But I'm conscious I haven't answered properly to your question. But it gives thoughts.
There's
yes?
one here.
You need a microphone, I think.
On its way.
I'm Raymond Bonnet from Queen Mary College. I wonder if you have any idea when the Curie family began to realise that the radioactivity was affecting their health?
It's a very good question, because the Curie family didn't believe at the outset that this could affect her health. And when Marie Curie was dying, there is a transcript that was given in a book by F. Curie. She didn't believe that radioactivity was something dangerous, that it was harm, it could harm someone, but could it kill someone? Didn't really believe it. She knew that something could happen, but she didn't believe it. I mean, there's a funny story where I think it was Langevin, but then Pierre Curie took a capsule of radon, and because Langevin manipulated some radon, and he got burned. He manipulated for 6 hours, and he got his fingers burned. And Pierre Curie said, well, never mind, I'm going to make the real test. I'm going to keep this capsule on my arm for 15 hours, and let's see what happens. Of course, it happened that he had the arm burned, and that the blister took many months to be cured. And well, I said, okay, I had that, that's fine. But the consciousness of the that it was bad for the health, I think, came extremely late. Even Irène Curie in the 20s was not conscious of that, which is strange because when they used the Curietherapy, the radiotherapy, they could see that there was collateral damages, but there was not a true quantitative measure of how dangerous it was, and they were convinced they were manipulating sufficiently small quantities that it could be dangerous, except that it was a nuisance in the lab, because when they were carried out measurements with the electrometer, when there was a lot of radioactive pollution, the noise that you would produce in the measurement was too high, so they couldn't conduct the measurement. So they would just broom the whole thing and start again. And of course, just to show you that in the first decade of the past century, they were totally unconscious. She was more frightened about X-rays, more frightened. But you can see in all the pictures I've shown and on what you can see in the museum in Paris, there is no lead protection of any sort, anywhere. Lead apron as we have, or lead gloves, or lead glasses. It came much later on when you had to manipulate heavy doses, of course. They sensed the need to be protected in the cobalt bomb, for instance, which was not cobalt, by the way, at that time, but they knew it was maybe harm. But the ingestion of radioactive material was, I can't answer your question because there is no trace, whenever what one can read, that they say at some point, hey, maybe this is dangerous, we should be more careful. Not really. I mean, I'm talking about Marie Curie, Irène Curie. I think Hélène Langevin was very conscious of that when she was working at Orsay, by all means.
Any more questions?
Apparently not.
No more. Well, there is just one more here, in the middle of the room here.
Sorry, my name's Peter Gallagher. I'm from the BP lab in Teddington. Just a matter of interest in the chemistry of the work. I mean, you say they had to use large quantities, many tons, to extract or prepare a gram material. Is there any history of how they actually prepared samples to extract and prepare the 1 gram from so much rock, or did they develop any techniques or any particular system to actually accumulate the 1 gram or prepare it?
I'm not sure I understood properly your question. What I can say is the process to extract decigrams was understood, chemically was understood, but it was very cumbersome. And so Marie, I had no time to explain that in my few words. Marie got acquainted with a French industrialist, which was called Armand de Lille, in 1904, because she said, I can't continue to do the work I've done in my shabby shed and continue to extract radium. I can't, I'm going to die. By exhaustion, not by contamination, by exhaustion. And this guy, he was acquainted with the pharmaceutical business, and he was producing, you say quinine or quinine, how do you say that, against malaria?
Quinine.
Quinine. He was producing quinine, and he was very fond of what Marie Curie was doing. He had a factory in the south of Paris, in the south suburbs, and he said, well, I can maybe process the stuff coming from the depleted ores and produce en masse some radium. I can do that. So the whole production, because the chemical, I would say mechanism was understood, was given to this company, and they produced the whole thing. And the Curies didn't want to license the process. They said, this is for the benefit of the humanity, we have to give it for free. So they gave it to the industrialists for free, and eventually this is how the Americans got the license free and the patent free, of course. And this guy, well, he processed tons of pitch blende, which was depleted uranium, and then he took some pitch blende, depleted pitch blende, and produced the gram quantity. But then there started to be a market for radium, and the market was led by the Americans who were conducting the price. And at mid-20s, you would buy a gram of radium for $100,000, the dollars of that time, which was equivalent at that time to 1 million gold francs. It was pretty expensive. So she completely led the production to someone else, which was certainly clever, but she wanted to have a unit of measuring the radioactivity called the Curie, and a Curie, which was something useful for physicists and chemists, would correspond to the radioactivity of 20 milligrams of radium. And those were produced in her lab, were not produced industrial-wise. So once the industry were able to produce, she wouldn't care anymore about the production. The Armand de Lille was even clever enough to have a lab installed by the factory so that the researchers working with Marie Curie could come to this lab and calibrate the sources, the radioactive sources, for their particular need. Have I answered your question or not? And today, to finish, I have absolutely no idea what is the stock, the world stock of radium. I have no idea, but I have to check. I have absolutely no idea if it goes by 10 of grams, by kilos. I don't know. I don't know. Because, of course, you can extract an immense quantity from the ore and presumably from radioactive fission products. No, from radioactive fission products you cannot. But from irradiated uranium, you can have other kind of radiums, I believe. So I have no idea.
Are there any more questions? Okay, well, if not, I'd just like to round up with a few thank yous, and thank yous to the organisers. I'd like to thank GSK, the sponsors for tonight's event. I'd like to thank you all for attending. I'd like to join me in thanking our speaker, who not only is giving us a very fascinating insight in his talk, but in the answers to his last questions, and perhaps if I could just comment particularly on the one on serendipity, he is somebody who has, if you like, walked the walk. He is somebody who, in promoting that serendipity, has spent a significant amount of his career trying to promote scientific cooperation and education internationally. So I'd like you to join me in thanking him for a very interesting talk tonight. Thank you very much.
Thank you very much. Thank you very much. Thank you. Well, thank you for your very kind words.
Thank you.
Thank you very much.
Very nice refreshment for you.
It's very kind.
That was fascinating. It was very interesting.
She's fascinating. She's fascinating.
I learned a bit that I didn't know.
Well,